Welcome to This Explainer. If you've been following the tech world lately, you know that modern artificial intelligence really does feel like pure magic. I mean, it writes code, it composes poetry, it can even diagnose diseases. But beneath all those incredibly complex, human-like outputs, there is a hidden engine running the whole show. Today, we're going to strip away the magic and look straight at the machinery to discover why the entire future of technology is basically bound by one fundamental mathematical reality. Let's open the hood. Okay, let's dive right into this. 90%, every single large language model you've ever interacted with, whether it's GPT, Claude, Gemini, you name it, spends over 90% of its computational time doing exactly one operation. It is not sitting there doing a bunch of diverse, complex logical puzzles. It is just doing matrix multiplication over and over and over again. And the scale of this is honestly almost impossible to wrap your head around. Just a single forward pass through a large model, just to generate a couple of words, can involve trillions of multiply and add operations. Training one of these things from scratch, you are literally burning through more matrix multiplications than there are stars in the observable universe.
So why does this one single mathematical operation shape the entire AI industry? Well, because understanding matrix multiplication isn't just a math lesson. It's the master key to understanding everything else in AI right now. It explains exactly why AI hardware looks the way it does, why these massive data centers need such specific cooling systems, and why the models themselves are structured the way they are. Scaling AI up isn't just a software puzzle anymore. It is fundamentally a physical hardware problem that is simply disguised as math.
Now, to really grasp this, we have to completely shift our mental model. When most people hear the word matrix, they instantly picture a static spreadsheet, right? Just a boring, flat grid of numbers. Go ahead and completely erase that from your mind. In the world of AI, a matrix is a dynamic machine. Think of it as a transformation. It's a function that takes in a vector of data and spits out a brand new transformed vector. You're stretching space, you're rotating it, compressing it, and reshaping that data to reveal hidden patterns. It's a highly active, moving process, not just some static lookup table. And this brings us right to the core architecture of neural networks. When you multiply two matrices together, you aren't just merging two tables of numbers. You are actually composing two transformations into one. So if you want to do transformation A and then transformation B, matrix multiplication gives you a single matrix that just does both of them at once. A neural network is simply layers upon layers of these transformations. Stacking layers is composing transformations. An entire AI model, from top to bottom, is really just one long continuous chain of matrix multiplications, bending and reshaping raw input data until it eventually becomes a meaningful prediction. This builds directly into the so-called magic of modern AI. The massive breakthrough that made large language models possible is called attention, which is the absolute core of the transformer architecture. But if you strip away all the dense academic jargon, attention is astonishingly simple. It boils down to just three mechanical matrix multiplications wired together. Step 1, you multiply a queries matrix by a keys matrix to get a relevance score. Step 2, you turn those scores into weights. And step 3, you multiply those weights by a values matrix to get your final output. And that's it. That is the mathematical soul of an AI's ability to understand context and the relationships between words. Let's ground this with one tiny example, and this brilliantly illustrates exactly how simple that fundamental math really is. Let's say we want to see how much one word should pay attention to another word. Our first word has a query vector of 1, 0. Our second word has a key vector of 1, 1. To multiply them, which is technically taking what's called a dot product, we just multiply the matching positions and add them up. So 1 times 1 plus 0 times 1. The result is 1. That single number, 1, is our attention score. It literally just tells the model how relevant those two words are to each other in a sentence. But here is where the harsh reality of AI kicks in. The scale explosion. That tiny calculation we literally just looked at, imagine that happening not just for two words, but for every single pair of words in a massive document. Now imagine it happening across dozens of different attention heads simultaneously. And then, imagine it happening across dozens of layers deep within the neural network. We are going from one simple dot product to trillions of them, all needing to be calculated at the exact same millisecond. This unimaginable explosion of scale is exactly why this simple operation becomes such a massive, defining bottleneck.
Which naturally brings us to the hardware. GPUs, or graphics processing units, were obviously not originally built for artificial intelligence. They were built for video games. They were designed to render millions of tiny triangles so your favorite shooter runs smoothly on your monitor. But mathematically, shading those triangles is really just a massive pile of matrix math. So, over a decade ago, AI researchers realized that the exact same silicon gamers used to heat up their bedrooms was accidentally perfect for running neural networks. Why? Because neural networks are exactly the same thing, just a massive pile of matrix math.
Modern chip makers have taken this accidental synergy and pushed it to the absolute physical limit. AI chips today contain something called tensor cores. A tensor core is a highly specialized circuit etched right into the silicon, whose only purpose in life is doing one thing extremely fast, multiplying small matrices together and adding the results. It doesn't do general computing well at all. It is hyper-optimized for this one specific task. And this is the exact reason why AI model training is measured in flops, floating point operations per second. Almost every single one of those flops is just a multiply and add happening inside a matrix multiplication right on a tensor core.
But there is a massive physical constraint here, a subtlety that most explanations totally miss. It's called being memory-bound. You see, you can build the fastest tensor core in the world, capable of a truly enormous number of multiplications per second. But if that chip is just sitting around waiting for the numbers to actually arrive from the computer's memory banks, all that incredible multiplication power just sits idle. A lightning-fast multiplier is totally useless if you cannot feed it data fast enough. You are ultimately bound by the speed of memory, not the speed of compute.
So how do AI engineers cheat physics to get around this? Well, they use a few incredibly clever tricks. The biggest one is batching. Instead of processing one sentence at a time, they process many sentences or inputs all at once. By doing this, they reshape the workload into much larger matrix operations. This ensures that once the data is finally pulled from memory, the tensor cores have a massive chunk of math to chew on, which utilizes the hardware's raw power much more efficiently. It's also exactly why hardware companies obsess over raw memory bandwidth just as much as processing speed.
Now, what's really interesting about this slide is another brilliant trick engineers use to beat this bottleneck: quantization. Traditionally, computers use 32-bit precision, which means very long, highly accurate numbers. But AI researchers realize that neural networks are actually incredibly resilient. You don't always need perfect precision. By shrinking those numbers down to 16-bit or even 8-bit precision, you sacrifice a tiny microscopic fraction of accuracy. But in return, your matrix multiplications happen dramatically faster, and you use half or a quarter of the memory footprint. You are actively trading away unnecessary precision for raw, blistering speed.
And the frontier of AI research is getting even more creative with this. I mean, if matrix multiplication is the bottleneck, what if we just don't do it? Enter mixture of experts models. Instead of passing every single piece of data through every single layer of a massive network, these architectures use a router. They route the data to only a tiny specialized fraction of the network, an expert. This means you get the incredible intelligence and capability of a massive trillion-parameter model, but you are computing far, far fewer matrix multiplications for any given input. They are literally routing around the math to bypass the physical hardware constraints.
Ultimately, matrix multiplication isn't just some abstract mathematical concept that engineers learn once in a textbook and then forget about. It is the singular, vital thread connecting everything in this industry. It connects neural network theory, the physical layout of GPU hardware, the efficiency of massive training facilities, the architecture of the models themselves, and the massive scale economics of the entire tech world. Every single time a new model gets cheaper or faster, it usually just means someone found a slightly smarter way to multiply matrices.
Which brings us to our final thought. The next time you see a headline about a massive new AI breakthrough, a revolutionary new chip, or a model that operates 10 times faster, you now have a permanent new lens to view it through. Don't just look at the shiny magic output. Stop and ask yourself, how did they multiply the matrices? Because underneath all the hype, that is exactly where the real revolution is happening. Thank you for joining me for this explainer. I hope this really helps you see the machinery behind the magic.